How's that?
Looks good.
Good.
Oh, how about that? Okay. What I'm going to talk about this evening is removing and restoring stars in deep sky object images or images of deep sky objects. And maybe I'll give you a little justification of why we might want to do that to begin with. Very briefly, let's see if we can get this thing to go forward now. Very briefly, what we're going to talk about is the process of star removal. First of all, just a little bit. That's not really the point of my talk, but it's going to be star removal of processed and stretched images of deep sky objects. And the stretching is somewhat optional, but it really, you should probably do it in all cases. How to remove the stars, what options you have for doing that are both easy and effective. Then a little bit about post-processing the starless image and why we do that. Well, I'll tell you that part right now. It's a lot easier to process images of a nebula, for instance, if there are no stars in there, because you can boost the color and the intensity of the nebula without saturating the stars, bloating the stars, or doing anything else bad to the stars. So if you get them out of there to begin with, so much the better. And then the hardest thing of all is replacing the stars. And I'll try to explain why that's both difficult and the way that I do it, which is mathematically more correct. It's not the only way to do it, I suspect. Okay, overall, overview here. Removing stars from an image. There are two programs available to us that I know about for removing stars. The first one is called StarNet, and it's version 2. It's just come out very recently. It's been around for at least a year before then. The second one is something called Star Exterminator, and it's at version 8. The developer of Star Exterminator has moved through improvements rather quickly, I think, as he is learning how to make an artificial intelligence program. Both of these are, in fact, artificial intelligence algorithms for removing the stars. And for different images, StarNet works better or Star Exterminator works better. There's no one right answer for all images you have, strangely enough. So I apply both to an image and see which one I want to work with, which starless image I want to work with, the one from StarNet or Star Exterminator. Replacing stars in a processed image. So once you have your starless image and you've processed it, it's not as easy as most people claim. The general statement is all you have to do is add the stars to the image. Processed image plus stars equals new image with processed image with stars. And that is not mathematically correct. It's not physically correct. It's not artistically correct. I don't know what else it is incorrect, but it's wrong. So why is it incorrect? We'll go over that a little bit. What needs to be done to do it better? And is there a PixInsight script that can do these things for you? And the answer is yes, I've written one. Okay, the star removal battle, StarNet 2 versus Star Exterminator 8. Both tools use artificial intelligence, as I've said, and they're very hard to train these artificial intelligence programs. The developers of these two programs had to spend countless hours painting out stars and images, carefully painting them out and showing the artificial intelligence program, this is what the star looks like with the image looks like with stars, and this is what the image looks like without stars. So when I show you a image with stars, you, as this artificial intelligence program, turn it into one without stars. And that's what they both attempt to do. StarNet 2 is a standalone tool. It's free. StarNet 1 was embedded into PixInsight. I'm not sure StarNet 2 will ever be put into PixInsight. largely because the license that the developer has posed for that particular tool is rather stringent, and PixInsight is an open source program, and StarNet 2 is not. Star Exterminator lives inside PixInsight. The developer of that program was able to write the code to make it fit into PixInsight, I think with a little bit of help, but mostly on its own. It has a modest cost, whereas StarNet 2 is a free program. Okay, here's what the issues are for both of these programs. In green are the things that both programs have pretty well mastered, and in white are the things that remain to be mastered by these programs. And future versions should get a little better at each of these things left in white. I won't read all of them, but poor results on linear images has been overcome. Both programs can do that. Star Exterminator does it automatically by just telling it it's working with a linear image. StarNet, you have to convert the image to nonlinear using a certain tool, and then or a certain sequence of events of tools, and then convert it back after you take the stars out back to nonlinear. I really don't see any point in working on images in the linear state. It doesn't seem to help your image processing. At least it hasn't helped mine. Both programs have trouble with stars that are very bright, and they both have problems with stars that have spikes. In fact, StarNet is a little better at spikes than Star Exterminator. There's incomplete removal of stars on bright backgrounds. That's been overcome by most of them. Small stars sometimes evade removal, mostly in Star Exterminator. StarNet gets most of them. Small galaxies are removed, sometimes accidentally, and the inverse is true there. StarNet tends to remove them when it shouldn't, and Star Exterminator tends to avoid them. Galaxies aren't damaged too badly now by star removal. The latest versions have overcome that. I'll show you an example later on. Globular clusters are still a pain. I just finished processing my first image with globular clusters and tried star removal on it, and was not at all pleased with the results. So I went back to old-fashioned processing in the presence of stars. Sometimes the patched areas are inconsistent with the surroundings. In StarNet, they tend to have a crosshatch in them sometimes, and also, strangely enough, star donuts around the removed stars, probably because the training data set used very, very small stars. Sometimes the noise in the patched area, you remove the star, you put in a patch, that patch doesn't have the same noise structure as the surrounding image has. That's been overcome to some degree by both programs. And star halos, like they say, when you remove the star, you leave a halo very often. Okay, so real quickly, let's look at the battle between StarNet and Star Exterminator. Here's the image I'm going to start with. Notice these big bright stars with spikes and lots of little stars. And if we try to take that image back to when it was linear and just apply these things blindly, Star Exterminator on the left and StarNet on the right, you can see that in the linear state, Star Exterminator does a much better job, not leaving all these little strange features in black where the stars were. But as I said, you can force StarNet to overcome that. I won't go into how or the details of that, but I would be happy to communicate with anybody about it if they want. Okay, when you stretch the images and apply it, now StarNet, to me, looks to do a little better job than Star Exterminator. They both do a quite credible job. Here's one small star in StarNet that didn't get all the way removed. And here's a big monster in Star Exterminator that didn't get removed. So what do? Well, you might go back and try to patch these things up. And I've tried that. And every time I've tried that, when I put the stars back in, I get something I just really don't like at all. Maybe you can figure out how to patch them better than I can. But if I see something like this now in my image that I've used Star Exterminator on, I leave it, do my stretching, do my processing, and in the end, maybe try to fix anything that devolves from that star being more or less left in. Okay, there's also these convenience issues. As I said, StarNet works outside of PixInsight, where Star Exterminator works inside it. If you're not using PixInsight, that's no big deal. You can use StarNet outside it. I think you can also use Star Exterminator outside. I haven't tried it, but I believe that's true. Star Exterminator also works in Photoshop. StarNet, you export a 16-bit TIFF to operate on. I don't know what internally Star Exterminator does with the image, whether it works in 16-bit or 32-bit. It'd be nice if it does 32-bit, but I'm blind to that information right now. Okay, there's no single best choice between StarNet and Star Exterminator, unfortunately. And I'll show you some examples where I've used StarNet and some where I've used Star Exterminator in the following example of star replacement. Okay, so the meat of the talk, the thing I really needed to get to was star replacement. And there's a simple way, as I've indicated, you just add the stars back to the image. You take them out, isolate the stars from the background mathematically, very simply, and then you just add them back in after you've processed the image. But there's a better way, because the first way doesn't maintain the star colors or intensities, and the second way does a better job of doing that. So say we take an image and we color calibrate that image, and we've stretched it and it's color calibrated, and we're going to remove the stars. And we can use one of those two programs, or if you know of something else, you can use that. We post-process the starless image. That is, we enhance the colors, we stretch further, maybe contrast in the image, color contrast, reduce noise, sharpen it, do all these things to it. And then we want to put the stars back in the image. And when we put them back in the image, we want them to have the same color calibration that they had when we took them out. So the difficulty is star colors shift with the background hue, shade, or tone shifting, and with saturation shifting. So that you can't just add them back in, because you're not adding them back into the same thing you subtracted them from, because you've changed that image in your image processing. Stars acquire textures from the underlying image in some cases. My method somewhat overcomes that, although not perfectly. Star shapes can become distorted because of the addition, simple addition, and we need a way around that. Bright stars are often not transferred to the image of stars only, and or only dimly so. That's problematic, to say the least. I'm not sure what to tell you about overcoming that if you encounter that problem. I haven't found a way to overcome it. Star spikes are often lost and distorted, and star halos arise in both methods. If you put the stars back into an image that you've brightened considerably, the star halos will be large and unsightly. And I've written another piece of script that helps remediate that a bit, but it's still a remaining problem. So here's an image that we're going to call the original image. And I want you to notice this yellow star here and these bluish stars in the image. So there's yellow and blue stars. Maybe this is a red star in here, for instance. If it's not noise, this one looks like noise, but let's say this is a red star. And we're going to call this our original image. And we're going to remove the stars from it. And we're going to process that image. So this is the image with the stars removed by Star Exterminator. Now, all the places where the stars were are now covered with patches of some kind or another. They're color patches intended to match their surroundings. Here, for instance, is a patch over a star, and you can certainly see it here. Another one here, certainly one here, and these big ones here and here, and many others. Even the little stars have patches that if you looked very closely, you'd be able to see them. So we're going to call that, by the way, Starless 0. I can't go back there. We're going to call this image Starless number 0, sub-0. Okay. Now here it is. Here's that image Stars 0, and here's the stars that we took out of it. We get these stars by simply subtracting the starless image from the original image, the one with the stars, and the difference is what was taken out of the image, which are the stars. Now, if you look at this image, you can clearly see blue-green stars in here, even kind of greenish stars. That blue star in here is red. The colors are all wrong. The yellow star is blue. This is because we subtracted them from a patch, and the patch wasn't there when the star was there. That star light was pretty pure and not influenced by a patch that is now underneath it. The spikes are also pretty ugly, but we're going to find we can't do a lot about that. Okay, so these stars are bad. They don't look like that stuff too much. Okay, whoops. Let's see, I think I went too much. Okay. We can now process the starless image. So this is our starless image, and we're going to process it, increase color contrast, intensities, and things like that. And pardon the fact that this is grotesque. I want to make a point in this presentation about the fact you can't just add the stars back in. So I've really messed with that background as best I can. So this is simply the starless image, boosted, colors boosted. I haven't tried to do anything particularly impressive with the image, just made an image that has more color, more intense colors, more diversity of colors by using color contrast and more detail. And we can certainly see where the stars used to be in here. So now if we're going to add those back, remember this area in here was all pretty much pink. Now if we add a star back to this, we're adding it back to blue, and we're not adding it back to pink. And the star was already had a color change. So here's what happens. These are the stars. Some of them you might want to look at here. And here's what they look like over here. For instance, these stars here are fairly blue in the original image. Well, they're very blue here, and they don't even really look like stars. This is kind of a whitish star, maybe a little tinge of blue. Here's a green star because we've added it back to a green background. Here's some white stars down here, and these also are blue, now blue stars. So all the star colors have been distorted because we've done simple arithmetic, and we haven't taken into account the fact that the background we subtracted them from is not the background we're adding them back to. Okay, So there is a better way. And this is an illustration of a better way. This is really a zero approximation to the better way. I'll show you results with the full method later. But at least here, this white star, for instance, or this bluish star, whitish blue, I guess, is retained. These whitish stars in here are whitish again, and so on. These down here are also whitish stars. This yellow star down here is yellow. The stars up here that were green in the previous image are now no longer green. So there is a better way to do this. And as far as I know, other than you and me, by the end of this evening, we're the only ones who know how to do this. So when stars are removed from the image, the colors change because they're subtracted from the patches in the initial image. And we saw just the stars only image, which had stars with strange colors in them. When they're added back to the starless image, their colors are changed again. They're not restored, they're changed again because they're added to an image that has been processed and changed. So how would we get the modified image to give us back stars more or less the original? Well, it's pixel math. And I'm not going to go through all this. I'm going to just kind of explain that the stars we got are simply the image that we started with minus the starless image. So that's straightforward. The stars that we want the corrected stars are these stars we get from simple subtraction plus something that corrects for them. And this is not going to be a unique equation. This is one I thought up because there's issues with noise, and this equation kind of helps with noise and a few other things. And what it is in fact, you're taking the starless image and you're multiplying it by these stars by an if fact. This is actually an if statement in here. If the stars are greater than the median plus 3 standard deviations, that is, if they're greater than average noise in the image above the average brightness of the image, then you multiply by the initial stars. If not, you just use the initial stars straight out. Otherwise, you multiply the starless by the stars. Interesting, but whatever. Okay. When the stars are met, these new stars that we just made in the previous slide are put back into the image with an equation like this, which takes the maximum value of the stars we just made in the previous image minus the starless image, or 0. It's not intuitively obvious why this works, and I'm not going to go into a long explanation of it. Partially works because I did it wrong so many times. Eventually, I got around to figuring out how to do it right. So we reach a final image simply by adding the stars to the above equation and say that the restarred image is some factor, arbitrary factor, some factor that boosts the intensity of the stars, plus the stars that we've modified twice now, so stars 2, plus the starless image, and that'll get us back there. It's not a simple, straightforward thing, and that's why I made a script. And in the script, which I'd be more than happy to share with everyone, we take this unmodified starless image. That's the one we got by applying StarNet or Star Exterminator. Our modified image, that's the one after we've processed it and changed the colors and changed the intensity and the sharpness and all those things. And then this is the image that we extracted the stars, the initial extraction of the stars. Put those things in. We can control the brightness of the stars in the image. If they're saturated, too many of them are saturated, we don't like that. We turn this down. It's a multiplier, so it makes the stars a little dimmer relative to the background. We can actually control star halos a little bit. I've had ones where In fact, you want to be a little bit below controlling the star halos. And this thing goes up to like 400 here. And I've worked up in this range where there were big star halos, and you can knock most of them out by that slider going way up. And all that does is make an area around the star where it suppresses colors. All right. There are a couple other options in here, which I generally don't use. This rescales the image between 0 and 0.94 if you've blown out all the stars. But if you do this, chances are the nebula is going to be faint again, and you'll have to use a star mask and simply boost the nebula up. And that's pretty easy to do. And sometimes that's the best option. All right, here's from my script doing the stars. And I think if you look at the before, this is what the original image looked like, and the after. You pick out this one here. It's obviously not as white as those stars, so there's some color in there. What else we got? Star over here is a yellow star, and after you put it back in, it's yellow as well. And you can always put a mask over this final image and boost the color of the stars, and I do that very often. And as I said, you probably would never make an image as enhanced as that one is. Okay, so this is a case where I applied StarNet to a galaxy. And you think, geez, a galaxy is made up of all stars. It's going to wipe out the whole galaxy. Well, it didn't. And furthermore, it left some of these other galaxies that are around it intact as well, strangely enough, because the artificial intelligence was taught to what a star looks like. And those things don't look like stars. So it left them alone. I think that's pretty remarkable, frankly. Here's an image. This is one of my latest images, and you may have seen it already. This is one that I processed by removing the stars, boosting the image considerably. The deep sky object, which is in fact a dark nebula in this case, or dark nebula and bright nebula mix, and then putting the stars back in. And I think using my script, and I think by and large, it's hard to tell that the stars were replaced in the image. So that's what I currently do with DSOs when I can. I hope some of that made sense, and I'd be happy to answer some questions. That's not a slide I wanted to show. Okay.
Alex, did you say that the Star Exterminator is now working better in the linear mode?
In the linear mode, Star Exterminator does pretty well. But actually, internally, what it does is it stretches the image, takes the star out, and then unstretches it using the same rules that it used to stretch it. So it's actually doing it in a stretched image. It's just not showing you that intermediate step.
Well, tried again. The few times I tried it, I got ugly results.
You mean Star Exterminator, you got ugly results?
Yeah.
On linear images? Yeah, like I said, I started out trying to do it on linear images and decided there's nothing gained by going to linear images. So I stopped that. But if you don't have questions now,
I have a question.
You can always write me, and I'd be happy to share any knowledge I know. See, I was a teacher, so I have to share.
Alex, I just have a little technical question. I am new to StarNet, and the version that I downloaded, I think it's StarNet, is integrated with PixInsight.
That's StarNet 1, yes.
No, StarNet 2.
I have that experience as well. I'm looking at it now.
It gets integrated, but you've got to install it.
Yeah, you have to install. You know, there were some instructions, which what I'm wondering is it the same thing you're talking about? It seems to be.
I didn't see any way to install StarNet 2. The instructions I read when I put it in, which is probably about 2 weeks ago, maybe 3, said it only functions externally to PixInsight. So maybe he's rewritten it to go inside, but I didn't see that.
Yeah, there's a YouTube video now that you can go check out, and the installation instructions are there for it.
Okay.
So Alex, in one of the early steps, you subtract the starless image from the beginning image. Does that in and of itself leave you with subtractive colors for the stars?
Yes, it leaves you with colors that are not right immediately.
But
And-
are those the subtractive colors because of the effect of the background being what's left over after the stars are removed?
It's because, yeah, after you've done that subtraction, or when you've done that subtraction, you've subtracted it from an image that's already been altered. That is, you put those patches in where the stars were, and those are colored patches. So you're subtracting a star of the true color in your first image. You've color calibrated it, so it's a true color star, and you're subtracting from that true color star a patch that has been put into the image, a colored patch. So you get the wrong color stars. And
Not necessarily the subtractive color, but something, because
right.
the yellow star looked like it turned blue.
Yeah, it's a shifted color.
Yeah.
It's not necessarily. I think it goes toward the opposite color, the subtracted color. How far it goes depends on the nature of the patch and the color of the star and things like that. In Star Exterminator, there's a checkbox where it will make a star mask, or it'll make the stars for you. It does that subtraction, but that's all it does is a subtraction. It doesn't correct those star colors either. So whether you do it yourself or whether you have Star Exterminator doing it, you still get those changed color stars.
Yeah, what I found is that the Star Exterminator is a plug-in for Photoshop, and you can remove the stars using it on a stretched image, and then blend it back into the original image as long as you've made the starless image slightly brighter. And you can use the brightness blending so that the starless enhanced image covers over the original image, and that seems to work pretty well.
Yeah, I haven't, being a PixInsight person, I haven't tried any layering methods or anything like that. I mean, even if you use anything that there's another way to do this whole thing that to me doesn't work well either, and it may be my lack of patience. But of course, you could copy the stars into the original image using a mask that says, basically, if the mask is transparent here, use the star. If it's not transparent, use the underlying image. And that would also get you the right star colors. But it's very hard in that for me to make that mask fit tightly all the stars of all the sizes. And I always end up with black halos around it, or stars that are distorted or something else. And so I found that this method gets me where I want to go. And I have to say, though, I am not a Photoshop user. It confuses the bejeebers out of me, and I run away and hide.
Hey, Alex, just a quick question about whether or not you've ever tried to recalibrate the star mask, or the starred image, if you will, the subtracted star image. Have you ever tried that?
Yes, I have.
And does it work?
Yes and no. If you recalibrate, you can get the star colors back, but of course, in that recalibration, it shifts the nebula colors.
I'm wondering if you just did it on the since it's a plate solve, I'm wondering if you could get away with a calibration on just the stars and not the nebula.
I don't know. I've never tried that.
Okay, yeah, interesting. Worth an experiment.
Yeah. In some of these cases, you've shifted the stars a long, long way from where they are, like right here. And you know, that was a pretty much a light blue or white star. And I'm not sure whether, given that star's shift, and these stars went green, and you know, whether you're going to get them all back the same, or whether it seems to me, you know, I guess it's different if they were on this greenish background, and then the others was on a reddish background, and these were on a bluish background. What you've subtracted from how you've shifted the stars in the process of separating them from the image, the starred image, is you've shifted them all different amounts. So when you try to put them all back, I'd be surprised if they get back to where they were, all of them. Don't know. Maybe worth a try.
All right. Well, you've certainly given us a lot of stuff to chew on and think about.
Okay.
Any other questions? All right. Well, continuing on with our theme of pixel math, let me share my screen. Can everybody see that? Okay, this is an image, and I'm just showing it in Maxim DL. And you should be able to see that this is a sub-exposure that something happened to. A cable dragged, or the wind blew, or something. But if you blow it up a little bit more, you can see that the stars are kind of misshapen, and they've got some little extra tails on them, indicating that, you know, something bumped in the night and caused the sub-exposure to be kind of damaged. So if you've got, you know, a couple hundred sub-exposures, you could say, well, I'm just going to toss this one. But if you've only got a few sub-exposures and you want to not just delete the time, you know, the amount of time that you spent on this sub-exposure, there's a kind of interesting way to work on this. And this isn't my technique. Those of you who have been reading Astronomy magazine for over 10 years probably remember about 10 years back, Adam Block wrote a column in there called Astro Imaging. And this is a technique that he introduced, you know, probably 10 or 15 years ago. And I use it every so often, and I thought it would be something useful that others might find helpful. So the question is, you know, what can you do to salvage this particular exposure? So I'm going to show you the basic thing that Adam Block set up a few years back. And basically there's 5 steps here. The first step is to find a good frame that matches up with the damaged frame or the defective frame. And you usually want to have a frame that's taken through the same filter around the same time, or as close and possible in the same time. And then you register those 2 frames together. If you've been dithering your sub-exposures, you need to do that. And you want to use the good frame as the reference frame, and you want to align the one that's messed up to that. And then you make a duplicate of the defective frame. And then the pixel math comes to the rescue once again, in that you subtract the good frame from the copy of the defective frame. And then using pixel math for the last step, you subtract that defect. What's left over from step 4 is basically the unwanted signal that's in the defective frame, the little tails or the misshapen stars, or even a satellite image trail. And then in the final step, you apply pixel math and you subtract the defective image, the copy of the defective image, the noise as it were, from the original defective image. And that seems to work pretty well. And let me show you some examples. So here's our defective image. And you see I've got a good image. This is the good image. And if I flip back and forth between them, you can see that they're not yet aligned. So the first step is to align those 2 images. And again, this is something you can do in most of the software that's available for image processing. I'm just going to dump those two into the alignment box in Maxim, and then tell Maxim to overlay the images with the good image as the reference image. And it does that. And now when we look at the defective image, you can see that switching back and forth, they're now aligned. Does everybody see that? Okay, so the next step is to select the defective image and to make a duplicate of it. And we'll simply make a duplicate of that image. So now we have a copy of the bad image. And now what we're going to do is apply pixel math to this image. So we select that image and select pixel math. And the pixel math in Maxim DL is pretty simple. It's just adding, subtracting, multiplying, dividing, and you can scale things as well. Let me scale this back to 100. So we take the copy of the defective image, and from that, we're going to subtract the good image. And when we do that, what we're left with is the noise, the stuff that is in the defective image that we don't really want. So we go back and select the defective image, and then again, pixel math, but this time we're going to subtract the copy, and voila, we now have an image that looks very similar to the good image. You can see most of the defective stuff is gone. And that's the trick. Any questions on that?
Yeah. So the devil's in the details there. Yeah. Can you show the before and after of the last two images again? Because I think if you zoom in, you can see the artifacts that are left over. So it did a great job on the stars, but I'm not quite convinced that the other details, so like if there were galaxies there or nebula or whatever, that we would have gotten a clean.
Okay, well, here's a 400%.
Okay.
So there's the original. Here's the good image. Oops, they're not in the same place.
Whoops.
I must have moved something, I'm sorry.
It's a pretty cool trick. No question about it, especially if you're aiming to, to deal with their stars and guiding problems or what have you. Why wouldn't you just take your best frame, okay, and then do this trick to every other frame, right, to get rid of all of this stuff in all your other frames. This you could take this to an extreme and say, I'm going to write a script that takes my best full width half max and rips through all of my images, subtracts everything else except from for the reference frame, and does this trick to every frame. And it seems like something is lost in the translation there, because that starlight that's in this signal here where things have been shifted has got to also impact the resolution of your galaxy and the resolution of your planetary nebula or any other extended source, right?
If you think
No, it doesn't.
I think Doug is entirely right. Let's say we just had in a picture here, and there was an airplane, and no, that's not doing the airplane. A nebula, a nice round circular galaxy or something like that. You align those two images, the galaxies align, you subtract them, and they go away, and then.
No, only the noise goes away.
Now, see that, but that's another problem, because when you subtract two images, now you've algebraically affected the noise, the true noise in the image, the shot noise and the random noise is also.
It does a great job of removing noise.
Well, but you're not supposed to be removing noise at this point, because you're going to take this image and stack it with all your other images, and now it's not going to have the same noise structure as your other images.
It'll have less.
Yeah, it'll have less noise than your other.
It'll have different noise, I guess is a better way to say it.
It'll have less noise in the background. We're talking about background noise, not this jiggle the scope.
Let's say there's some artifacts there. If you're gonna throw this in with the big stack, aren't those artifacts gonna go away?
Yes.
All right, so maybe
these are
let me-
Sub-exposures.
Okay, so let me bring it to another way of thinking of this. Think about adaptive optics for a moment. This is sort of poor man's not adaptive optics, because if you think about what adaptive optics does, it's going to take based on a PSF, and it's going to say, where's the energy? And let me take all of the energy and put it back where it's supposed to have been. And it does this very rapidly. This is not that case. We're taking a defective image and we're subtracting sort of the difference between it and our reference image, but we haven't really put the energy back where it belongs. We just threw away the energy that was going in a different direction. And I'm not quite sure that isn't going to have an impact on the extended objects, right?
Let me say one other thing. I agree totally with Doug, but let's say these images highly vignetted. When you subtract the image from another image, the vignetting is depressed. And so
These are
now,
all calibrated images.
now you calibrated and flattened, because
Yep.
okay, if you
Calibrated.
did it at that point, then you might not get that. But I just it just is affecting the noise structure of the
Well,
image.
here are the two of them I've got them lined up now. So you can see this is the original
Yeah.
bad one, and this is the good one. You can see the good one's still slightly better. And there's some hot pixels in the good one that don't show up in the bad one because of course they've been subtracted.
Okay, wait. So those artifacts are there. Go back to that one. Now stop right there for a moment and
Okay.
slide your cursor to the right on the very bright star that's sort of middle right. Up and to the, no, up and to the right. Keep going right, to the right. Yeah, there you go. That one, that star. Look right below that star and see that artifact. That's the little cloud right below. No, I'm talking about here. Right there.
Okay,
that
well, I'm
cloud.
glad you brought that up because I'm going to
Yeah.
show you another example.
Okay.
Okay, let me close these.
By the way, those artifacts appear in other stars as well, right? The ones further to the right, you can see another cloud there.
Yeah. So let me open up another one and show you an example where this doesn't work and what you can do about it. Okay, so here's one that's a little bit more of a mess up. You can see that something bumped the scope or something here, and there's quite a bit of extra noise in there.
I gotta tell you, I'm throwing that one away, buddy.
And here's a good version of that same. Okay, so the first thing we want to do is we want to align the two of them. Again, I'm going to dump them in a box and align them. And now you see the good one and the defective one. And the bright stars are aligned. In fact, all the stars are aligned. Okay?
Mhm.
So we make a copy of the bad one. This is our copy. This is our good one. So from the copy, using pixel math again, we subtract the good frame. And we're left with the noise. And then we pick the defective frame and subtract the noise. And this is what we're left with. And this is what I think Doug was referring to in the other image, in that the subtraction didn't completely get rid of all of the artifact, all of the unwanted signal. Everybody see that? You can see there's still some traces here, but there's a way around that. So let me put the bad one back and get rid of this. So the way around that, using this same technique, that we've already aligned the two. So again, I'm going to make a duplicate of the defective one. Here's our duplicate. And now when we do the pixel math, you notice that there's the ability to scale either the bad frame are the good frame. And if I bump up the bad frame, since we didn't get rid of all of it, I'm just bumping it up to 140% here and subtracting the good frame. And you can see now there's more noise than there was before. In other words, because the images didn't match perfectly before, by bumping up the noisy signal and subtracting the good signal, we're left with more noise. And then again, using the same technique we did before, picking the bad frame and subtracting the copy, we get the good frame. So now we have similar results for the good, the old and the new. All right. So there are, by using pixel math, there's a pretty easy way to salvage these subframes so that you can use them in your stack if you've devoted a lot of time to them. For example, if it's a 15-minute integration through a narrow band filter, and you don't want to throw away 15 minutes worth of imaging time, this would be one way of going about finding some of that information.
How much of that would just drop out just through a regular integration?
A lot of it would drop off if you had a lot of sub-exposures and you used a statistical method like sigma clipping or something like that. Of course, you get rid of it a lot of times. So if I have 20 exposures and one of them look like that, I might just leave it in there and see what sigma clipping does when I cut the clipping down to maybe one standard deviation. A lot of times that would take care of the issue. But this seems to me to be an easy way to salvage a sub-exposure that might otherwise get tossed.
Hey, Greg,
Yeah,
pardon me if this is a dumb question because I'm tired tonight, but if pixel math worked perfectly, and when you did the subtraction process, you identified how your flawed image differed from your reference image.
that's what we're doing.
And you take that subtracted result and subtract it from the flawed image. Aren't you in effect just creating a copy of the reference image?
No,
Why? This is where I admit that I may be tired here.
well, because you're subtracting the noise. The unwanted signal is what's left after you subtract the good image from the bad image. We're just making a copy so that we have something to then go back and apply to the original defective image.
Well, but that's what I'm saying. If you really looked at it in a micro sense, one star, one perfect star and one defective star image, you identify the difference through the pixel math process, you subtract the difference from the flawed image, and then you're left with a perfect star image. But it seems to me if pixel math works the way we think it does, you're left with a copy of that perfect star image. Yeah, it might help the integration and noise and all that, but in a sense, it's a long way of creating a copy of the reference image.
No, it's not a copy because you're not subtracting these stars that are okay in the reference image. Remember, if we back up here, remember these stars are okay. They don't get subtracted. Okay, what gets subtracted is the other stuff.
Well, if you have a flawed image, say from a flaw in tracking or something, then how do you have a percentage of perfect star images in your otherwise flawed image? How are some defective and some not?
You're just subtracting. It's kind of, you could do this with a satellite trail. In other words, if you had two images and one of them had a satellite trail in it, you could do the exact same thing. Okay. The only thing that would be different in the two images after you stacked on the stars would be the satellite image.
Right.
So when you subtract the good image from the satellite image, all you'd see left was the satellite trail. If you can try this, with any program that supports pixel math, So I would suggest that you go back and play with it with whatever your software of choice is.
Well, I'm trying to think through the pixel math process, and it seems like if you took your result, which is the flawed image with the perfect image subtracted out, you take that result and
There it is.
you subtract it from the flawed image.
That's
and
what we
you're
do.
left- Yeah, and you're left with a resultant, improved image. And then you subtracted that from the reference or subtracted the reference from that, you'd be left with a blank image, wouldn't you?
Yeah.
That's exactly right. That's
Yeah.
mathematically correct. If you write a simple equation that says, first of all, you've got a bad image minus good, B minus G. And then you take the bad image and you subtract the quantity bad minus good. Then you end up with good. And so all you've done is reproduce the good image.
That's how I was
No,
perceiving it.
no, you still
And
have
yet-
still different images.
That's what they only
Yeah,
that the two images somewhere something's going wrong, but they in the noise of
So
the
theoretically, Alex,
I mean real noise, not this Jiggles telescope, but I mean the background noise is what's being affected, and that's what makes the images look a little different because those aren't lining up perfectly. They're different in the images. But
yeah, so I think I agree with you, Alex and Kevin. But if you look again, Greg, at the difference between your final image and the reference image, you see the ghosting, right? And so I don't know how far.
All I see are hot pixels.
No, I see quite a bit of. Leave it on the finished right there. Look at all that ghosting that's going on, which is the leftover signal from the trails, right? This is not the good one. I'm talking about the other one. Switch back to the other one. That one. Is it just me, or do other people see that those trails are still there? They're less than they were.
There's some ghosting. Here's a trail right here.
Right, exactly. There's a bunch of trails still there. So technically, although I agree with Alex and Kevin that you should theoretically be able to what you're really generating is back to another copy of the reference. We're not actually getting there because you still got a lot of ghosting in your final correction. So something
That's
else
because
is going on.
I didn't bump up the scaling quite enough.
But
That's
what-
why I wanted to show you this one where if you also do a multiplication before you do the subtraction, you can affect how much of the ghost image is there or not there. And of course,
But aren't you asymptotically approaching the reference image?
No.
Yeah.
That would be only true if you assume that the intensities of the stars in both of them were identical. If there's something, if the bad image has got some kind of a different intensity, a lower amount, you won't be duplicating the original image.
I think you guys are overthinking this.
No,
Think of it as a pixel, a pixel well. All of our image sensors have well depth, and every image that we take is going to have a little bit different well depth at each one of those points. So the images are, even if you subtract them, they're not going to be the same because the well depth of each pixel is going to be different from one image to the next.
That's the noise though. So what you're doing is you're saying everything, you're duplicating the original image, but the noise in the duplicate image is different. And that's basically what it's saying.
No.
Yeah, and
If we had more time, I would walk you through looking at the counts for some of these stars on the original and then the modified. And what you're going to find is they're very similar, but they're not the same as in the good image that we used to subtract to get the noise. Okay, so we're not making a copy of the good image. If it was that simple, you just make one good image and multiply it 50 times and then stack them, right? We know that doesn't work.
No, and that's because the stacking is taking care of noise. That's the issue. And so that's the only reason you stack images. If you had a zero noise image, you just take one frame And so you're getting the same image again, but with different noise.
Right, and that's because they were dithered to start with. Remember, the step
Just
one was
different
to
noise.
align the stars in order to do the subtraction. So we're aligning stars that, as Tom pointed out, where the stars were actually captured on different parts of the sensor.
Imagine for a moment that you had 10 of these frames, okay? 10 of your 15 frames were messed up and you have one beautiful reference frame. And this is a picture of a galaxy, okay? And the galaxy has been shifted left, right, up and down, all over. And I'm really suspicious that this works great for stars. I suspect this works terrible for extended objects.
Now, here's an extended object.
Yeah, so is this on the, this is the second image that we did, yeah? The one with the worst trailing?
This is the one with the trailing.
Okay.
And you can see there's some trailing in here still that you could get rid of by a different scaling factor. But, you know, here's your extended image and it looks pretty normal.
Yeah, I don't know. There's a lot of ghosting in there. It'd be interesting to take a, you know, it would take a little bit to really check that out, because imagine X and Y, right? You've got one direction. Imagine the worst case scenario where everything's going wrong. Somebody's kicked the mount and then the RA axis is behaving badly. You get all this smearing going on. You've corrected back to the reference image, but I'm not quite so sure this technique works that great on extended objects. I would really like to see
Well,
that
here's
a little bit better.
here's an extended object. This is the good frame.
Pretty good. Okay.
Yeah.
And here's the extended object in the frame that we fixed. You can see there's still some ghosting, which we could get rid of. What do you think?
The galaxy
This looks,
just like the ghosting. That's the problem.
I mean, it's a cool trick. There's no question. It's cool. Whether or not, you know, we want to trust it too many times, maybe saving a frame, you know, but I don't know, it'd be scary. In the extreme, I think you could imagine this going wrong.
I think
I
the
think
other
the
thing to
bottom
think
line
about-
is, if you put that image back in a stack, you've improved an image, you can use it in your stack, and you're going to have an incrementally better final result. That's how I see it.
you know,
Yeah, I'm not so sure that Sigma clipping wouldn't just throw it out.
yeah, that's the thing. The problem is with Sigma clipping coming into it is you should just throw out the bad image, because if that's the bad image, that's the one that's going to provide the Sigma clipping. It's going to donate to Sigma clipped image, the Sigma clipped part, more than any other image. Whereas you should be taking the good images and throwing away the bad pixels in the good image and keeping the good image, instead of throwing away all the pixels from your one bad image and then leaving the bad pixels in the other images unclipped. Throwing away, being very severe in blinking your images and getting rid of bad ones is really a much better way to control the quality of your final image than is Sigma clipping with all your bad images thrown in there.
So if we came back to Greg's original point that if you only got 10 frames, okay, and you've got nothing better than 10 frames and you're trying to salvage one of those bad frames, maybe I concur that this would work. The answer is get enough signal, right? Get enough signal and throw out your bad frames. That's going to save your life.
All right, well, we've pretty much covered that.
I just hope all of you realize what a great discussion this was. Energetic and opinionated and differing views, but so informative. Thank you.
So I've got a couple of announcements. The next month's meeting will be the third Monday of the month, and that's on May 16th. And you probably have already gotten an email from May Smith telling us that the TAAA is going to allow in-person meetings again. And so we checked, Tom Rolfsmeyer checked with the folks at Total Wine and More, where we used to meet before COVID, and they're still not having folks use their classroom at their location there on Wilmot. So until that's available, we don't really have to worry about doing anything other than Zoom. And at some point in the future, we'll have to decide whether we want to have in-person meetings at all or just continue with Zoom. But for the next several months, it looks like we're going to be confined to continuing by Zoom. Any questions?
So I guess we continue drinking on our own then.
You mentioned its location is on Wilmot? I thought it was on Oracle.
Wetmore.
Wetmore, I'm
Oh,
sorry, not Wilmot, Wetmore.
Okay. Oh, all right. That's what it sounded like.
Yeah. All right.
Hey, Greg, I wanted to just, echo Jeff's comment there. I really enjoyed your talk, and I think it very thought-provoking. So I don't want anyone to feel like, we challenged this too hard. We're challenging for all the right reasons, I hope, and nobody should be offended by anything that we say. So all meant in good spirit.
Well, good. And I can tell you that I use this technique quite often to get some subexposures back when needed. And it seems to work, and it adds to the total amount of exposure. So
Yeah,
all
definitely
right.
mind-bending.
Another question here. In
By
fact,
the way, Greg, before we leave, congratulations on your publication in Sky and Telescope.
Thank
Your
you.
image,
Yes.
well done.
All right. Thank you, everyone.
Bye.